Hey there, Azmir here, and today we are going to talk about image of a black hole, and this discussion will be based on a 1978 paper by Luminae over here. Now, without further ado, let's get started. So in this paper, a Schwarzschild black hole is assumed, which is non-rotating, of which we get the familiar line element on the top over there. Do note that this is in natural units for the G and C, and the value of Schwarzschild radius is 2m. Now, if we are to take advantage of the symmetry at the equatorial plane, we then find that the trajectories of the particle obey the differential equation right there in the middle there. Here, VR is the analogical potential and B is the impact parameter. If we want to find the value of critical V by differentiating, we find that VC is equals to 1 over 27m squared. Now, this value is important when we consider the accessibility condition on the left, on the arrow over there, of which if we put the value, we get the critical impact parameter, which is roughly around 5.2 m right here. Now, for a light that travels below that impact parameter, it will be captured by the black hole. If it's more than that impact parameter, it will be deflected, but it won't be captured. Now, with that differential equation, we can also consider the periastron and then the subsequent solutions, which involves the Jacobian elliptical functions. We finally get the relation of when B approaches BC, we get the equation on the top left of there. Now, we also consider that when it is deflected by mu, but it also orbits by 2 pi, 4 pi, 6 pi, 8 pi, and so on, then we get the generalized equation on the lower left over there, of which if it's infinitely circuiting, it becomes the value of BC. Now, this relation is significant because when we look at the contribution by differentiating with respect to the mu, which is the deflection parameter, we get the contribution, the nth contribution. So now with just a deflection of mu, which is B naught, we get a 0.1505 contribution. And with the value of BC, which is infinite circuit, we get the contribution of roughly 0. So what this physically means is that when we observe a bare black hole, at the radius of B naught, there's a ring of bright light, and at the radius of BC, well, it's total darkness. Now, understanding the bare black holes, we can finally include the accretion disk. For objects that is between us and the black hole, we will just see it as a pure projection, while as for objects behind the black hole, well, we can see it due to the fact that it undergoes weak deviation and the light ray bends towards us. So what this all means is that theoretically speaking, when we look at the black hole head on, it will look like the image on the lower right over there. Now, follow me for 1 second. So as you can see from over here, this green over here is the equatorial plane, and what you can see, the orange line over here is the pure projection, and the orange line on the whiteboard is from behind the black hole, of which the light ray is bent, and the light ray is also bent through the bottom. So finally, for a real black hole, there are gas on the accretion disk which orbits the black hole. Now with this, we must take into account the relativistic correction and also the Doppler effect. The end result of this is an image that looks something like this one over here. Now this one over here is a simulation done by NASA. Beautiful, isn't it? Now that is all from me. Thank you.